Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching your favorite series KCET 60 out of 60 in physics, where I am trying to help you to achieve your dream of getting 60 out of 60 in KCET 2025. And if you are preparing for KCET 2025 exam, then you are at the right place, and we have already completed our entire syllabus of second PU, and today is the last class for second PU main class. Okay, from next time onwards, whenever we discuss about second PU, we will discuss mainly about chapter revision, shortcuts, tricks, tips, etc. But today will be going to be the last question paper discussion, questions discussion for second PU chapters. We have completed the entire chapter. If you have not seen any of the videos, if you are visiting this channel for the first time, then don't forget to subscribe to our channel and then go back to the playlist section. There we have a dedicated playlist for KCET 2025 physics series, where all the videos, all the lectures that I have done is available, so you can watch at any point of time at your convenient time, right? So let's start with today's topic, that is semiconductor electronics. Also, I want to remind you that tomorrow there will be KPL number 8, KCET number 8, mock test 8, and there we are going to give you the question paper through our WhatsApp channel. If you have not joined our WhatsApp group yet, don't forget to click on the description below and join our WhatsApp group. Also, this week's syllabus is semiconductor electronics and nuclei. Okay, these two chapters will be important for this week's KPL. So if you have not prepared these two chapters, first go watch my videos or prepare before answering that question. You will have an entire day tomorrow. Tomorrow is a holiday as usual, Sunday, so you can prepare the topics and then you can answer those questions. Okay, but without any delay, let us start with the chapter semiconductor diodes, semiconductor devices. Now, when a PN junction diode is in forward bias, which type of charge carriers flow in the connecting wire? So I have discussed this. Only free electron flows in a circuit, no matter if it is a diode, no matter if it is a conductor. Only thing that flows is free electrons. Only electrons can carry charges. Okay, even though there are something called holes. Holes are nothing but absence of electrons. So even if I say hole is flowing, hole is actually not flowing. Electrons are occupying the holes. Okay, so main thing is free electrons. Okay, now a full wave rectifier with diodes D1 and D2 is used to rectify 50 Hz alternating voltage. The diode D1 conducts dash times in 1 second. Now what is the meaning of 50 Hz? If you remember, so 50 Hz means this is one cycle. This is called one cycle of input voltage. Okay, this is an AC input, right? So 50 Hz means this cycle is occurring 50 times and this cycle is occurring another 50 times. Both halves are occurring 50 times. Now if I say that diode, there is a full wave rectifier using two diodes, then diode D1 will be conducting for the positive half and diode D2 will conduct for the negative half, right? We have already know that. So how many times diode D1 will conduct? Obviously 50 times. So diode D1 will conduct for 50 times, diode D2 will conduct for 50 times. The total frequency will be 100, but the question is not about total frequency. Question is about how many times diode D1 will conduct. Okay, diode D1 will conduct for 50 times. Now let's move into the question number 3. The energy gap of an LED is 2.4 electron volt. When the LED is switched on, the momentum of the emitted photons. So actually this is a mixed concept question based on the chapter of wave particle duality, and they have mixed the concept with LED. Now as even though the exact LED is not part of the syllabus, this type of question still may come because dual radiation, nature of radiation and matter is still in your syllabus, and this is a basic concept. Okay, so what is the energy of the photon emitted? Energy of the photon emitted is 2.4 eV. Right, so energy of the photon emitted is eV when the LED is switched on. Now what is the momentum of the particle? So why we have to, what we have to do, we have to find the momentum of the particle. Now if you remember that wavelength lambda is given by h by p, right? So wavelength of the lambda is given by h by p, so momentum is nothing but h by lambda, right? So we have to find h by lambda. Now again, what else? We know that energy E is equals to h nu. H nu is nothing but hc by lambda. Okay, so from there we can write h by lambda, which is equals to p, by the way, is equals to E by c. So if you know energy and if you know speed of light in vacuum, that we already know, then you can find the momentum. Now E is given in terms of EV. Okay, so 2.4 EV. 2.4 EV means what is the joules? It will be 1.6 times 10 to the power of minus 16. Minus 19, right? And what is the C? C is 3 times 10 to the power of 8, right? So now you have to simplify. So it will be 3, 0.8, okay, 0.8 times 16. So 64 times 2, that is 138, 1.38 times 10 to the power of minus 19, and there is a 8 division. 8 division means it will go up and it will become minus 8. So minus 19 minus 8 is minus 27. Okay, so this is the momentum. So let us see. It will be 1.28. Sorry. It will be how I calculated it, I will explain in a while. Let me write the answer. So 1.28 times 10 to the power of minus 27 kilogram per meter per second. Now I said 8 is the 64. So how I got 8 from here? So if you remember, we had 0.8, so I removed the point. I just taken 8. Okay. I had another number was 1.6. So I removed the point here also. I made it 16. Okay. If you can multiply them, fine. Okay. I took 16 as 8 times 2. I found it easier in this way. Okay. Instead of multiplying 16 times 8, for that you have to remember, okay, 8, 8, 48. Okay. So that is fine. If you can do it, that is fine. But what I did 8 8s are 64, 64s are 2 is 128, 64 times 2 is 128. Now 128, how many decimals was there? One decimal was with 0.8, one decimal with 1.6, so 1, 2 decimals. Right, this is a way that there are different ways. You can use calculator, you can use your mind to train as much as possible, but for that you have to stop using calculators, then you can solve these questions easily. Now let's look into the next question. The resistivity of a semiconductor at room temperature is in between. So we have discussed that the resistivity of a semiconductor is 10 to the power of minus 5 to 10 to the power of 6 ohm meter. You remember that? Now here they have given the unit in centimeter. Okay, ohm centimeter. All the units are in ohm centimeter. Now basically what you have to do to convert it into ohm centimeter, you have to multiply it with 100, right? So it will become 10 to the power of minus 3 to 10 to the power of plus 8. Right, so you have to multiply it with 100 because 1 meter is 100 centimeter. So 10 to the power of 8 ohm centimeter. So this one will be less negative, this one will be more positive. So correct answer is this. Okay, you have to remember these values. These values are very important. Now let's move on to the next question. The forbidden energy gap for germanium crystal at 0 Kelvin, this is 0.71 electron volt. Very easy, very simple, right? So most of the questions after deletion of the digital electronics, most of the leftover questions are simple and easy. So I hope that there will be 3 to 4 questions coming from this chapter which will not be very difficult. Okay, there are few questions. I will try to answer that as well here in this discussion. Identify the incorrect statement. Okay, this is interesting question. When a PN junction diode is forward biased, the width of the depletion region decreases. Okay, correct statement. Okay, they have asked you to find the incorrect statement. Remember that. Okay, incorrect statement. So this is a correct statement. Depletion, width of the depletion region decreases, right? And slowly it becomes 0. When a PN junction diode is reverse biased, the barrier potential increases. Obviously, the new potential is V plus V naught, if you remember. So this is also correct. Barrier potential increases. A photodiode is operated in the reverse bias. Photodiode is not part of your syllabus. Okay. And LED is lightly doped PN junction diode which emits spontaneous radiation of forward biasing. Okay. If you consider C and D option, one of them is correct answer. So for this given question, photodiode operated in reverse bias is correct. So only option which is incorrect is this, and LED is lightly doped. It is not lightly doped. Okay, and junction diode which emits spontaneous radiation of forward biasing, it does not emit spontaneous radiation. It emits continuous emitting. Okay, so that is the thing of about LED. But this question it will not come, even though the first two parts, option A and option B, are in your syllabus. Neither photodiode nor LED are part of your syllabus. So this question will not come, but there maybe they may change the options of C and D and they might ask you a similar question. Now let's look into this question. 3 photodiodes D1, D2 and D3 are made up of semiconductor having band gaps of 2.5 electron volt, 2 electron volt and 3 electron volt respectively. Which one will be able to detect a light of wavelength 600 nanometer? Now, even though this question is not super relevant, but the question is very interesting, that's why I kept it. Okay, so basically what they have asked you that which one of them can be able to detect this nanometer. So you have to find the energy for this wavelength. Okay, so what is the energy of this wavelength? Energy of this wavelength will be h nu. Okay, and then you have to convert it into EV. H nu is hc by lambda. Okay, so what is hc? I told you in terms of when you are converting into nanometer and EV, okay, you can use 1240 for hc, nanometer times EV. Okay, so divided by nanometer, nanometer is 600. Okay, so this is in EV. So 0 0 cancels, 6 2s are 12, 2 point something. Okay, 2.6 to the 12 and 4 means 0.3. 0.6, sorry, 6 6 are 36. So 4 does not go, so you have to add a 0 here. So you will be 6, 2.06, right? So 2.06 almost approximately you can consider this to be 2.06 EV. Okay, so which of the diodes can detect? So to detect this wavelength, the band gap should be more than this. Okay, if the band gap is more than this, then only they will be able to detect it. Okay, so only D1, this will definitely detect, this one will not be able to detect because that is more than its gap. Okay, and this one will be able to detect it. Okay, so D1, only D1, not correct. Both D1 and D3, yes, this is correct. Both D1 and D3 will be able to detect this signal, whereas D2, which has a much less gap, will not be able to detect because it will not be able to, it will go above its limit, right? Now, this is also an interesting question. A 220 volt AC supply is connected between the points A and B as shown in the figure. What will be the potential difference V across the capacitor? So you have applied 220 volt AC, right? And this is a half wave rectifier. So half wave rectifier only rectify half of the wavelength, right? Half of the input is this. Okay, and you are getting an output of this. Okay, so this is the RMS input. If you remember, when we are talking about AC, the values are given in terms of RMS value, and if the value is given in RMS value, you should remember for half wave rectifier, the output voltage is basically half of the input. Okay, half of the input voltage when it is given in RMS value. So it will be 120 volt. So when the input is 220 volt for half wave rectifier, the output will be VI by 2. It will be 110 volts. Okay, simple. Now the conductivity of semiconductor increases with the increase in the temperature. Okay, this is for a normal semiconductor. Normal semiconductor's conductivity increases as we increase the temperature. That is the basic property of semiconductor, because for normal conductor, if you increase the temperature, its conductivity decreases. For insulator, it does not matter. Insulator does not conduct even in higher temperature, but for semiconductor, their conductivity increases. Why? Because both number density of charge carriers and relaxation time increases. Number density of charge carriers increases, number density of current carriers increases, relaxation time decreases, but the effect of decrease in the relaxation time is much less than the increase in the number density. The relaxation time increases. Okay, so relaxation time is, we know that when we apply electric field, okay, there is a time that is required for an electron to behave. Okay, so if the relaxation time increases, the current flows slowly. Okay, that is the reason for conductor to become less conductor. As we increase the temperature, the relaxation time is increases, so it takes longer time to relax. So that is why their conductivity decreases. For semiconductor, what happens is the number density of current carrier increases and relaxation time decreases, but effect of the decrease in the relaxation time is much less than increase in number density. So that is the correct answer. So relaxation time, even though it is decreasing, okay, the number density is increasing by so much that electrons, even though their relaxation time is decreased, so they are not they are reluctant to carry current, but still, because the number density is increasing so much that it has to conduct electricity. Okay, now a positive hole in a semiconductor is absence of free electrons, an artificially created particle, an antiparticle of electron, a vacancy created when an electron leaves a covalent bond. Okay, don't get fall in the trap. And okay, absence of free electrons, it should be correct answer. You don't read the complete question before answering. Okay, the absence of free electrons is not holes. Okay, holes are when an electron is taken out from a covalent bond, that is called a hole. Okay, be careful. Now question number 11, the density of an electron hole pair in a pure germanium is 3 times 10 to the power of 16 meter cube, meter inverse cube at room temperature. On doping with aluminium, the hole density increases to 4.5 times 10 to the power of 12 meter to the power minus 3. Now the electron density will be, so we know that at any case Ne times Nh equals to Ni. This is the intrinsic semiconductor, Ni square. Okay, this is the intrinsic charge density. So intrinsic charge density is given 3 times 10 to the power of 16. Okay, when it is doped, the hole density is given by 4.5 times 10 to the power of 22. So we have to calculate Ne. So from this equation we can write Ne is equal to Ni square divided by Nh. I guess there will be definitely a question based on this formula. There is a high probability that they will ask you one question based on this formula, because this formula is in your syllabus. Okay, now what is Ni square? Ni square is 3 times 10 to the power of 16 whole square. And what is Nh? H is 4.5 times 10 to the power of 22. Okay, so now 9 times 10 to the power of 16 means 32. 4.5 times 10 to the power of 22. Okay, so you will cancel, it will get 2. So 2 times 10 to the power of 32 minus 22, that is 10. Okay, so 2 times 10 to the power of 10 is the answer. Simple. Okay, not so difficult. Now let's move on to the question number 12. In the figure shown, if the diode is forward voltage drop to is if the diode forward voltage drop is 0.2 volt, then the voltage difference between A and B. So what is the question here? You have a point A, you have a point B, and if you see, there is a current flowing in the circuit which is 0.2 milliampere. Okay, the current flowing in the circuit is 0.2 milliampere, and there is a 5 kilo ohm resistance here. There is a 5 kilo ohm resistance here. Okay, so now they have asked you what is the potential difference between A and B if the diode drop across the diode is 0.2. Drop across the diode, that is the forward by the diode voltage, is 0.2 volt. Then what will be the potential difference between A and B? But first let us understand whether diode will conduct or not. Okay, diode will conduct or not. So if there is a 0.2 milliampere current, if you see, the current is flowing from here to here. So basically current is flowing in the direction of the diode symbol, right? So if the diode is in reverse bias, there will be no current. Okay, you can simply mark the answer to be 0. But here the diode is forward biased. So diode is forward biased means the current will flow. Now how can we measure the potential difference? Simple, ignore the diode for now. Ignore the diode for now. What will be the equivalent resistance if you connect one 5 kilo ohm, another 5 kilo ohm? Okay, this is the simplest way. So if you connect two 5 kilo ohm resistance in series, you can ignore this. There is nothing is associated with this part, so you can simply, this is a filter, you can ignore that. Okay, so only thing that is 5 kilo ohm, they are connected in series, though the equivalent resistance will be 10 kilo ohm. If the equivalent resistance is 10 kilo ohm, then what is the voltage difference? The voltage difference will be 10 kilo ohm times the current, V is equal to IR, right? So I is given 0.2 milliampere and resistance is given kilo ohm. Okay, kilo ohm means 10 to the power of okay, let me simplify this. I am doing it a little faster. I should go a little slower so that you can understand. So I is 0.2 milliampere. Milliampere means 10 to the power of -3. And resistance we have calculated 10 kilo ohm. 10 kilo ohm means 10 times 10 to the power of 3. So they will cancel each other. So you will get 2 volt. 2 volt is when the diode is not there. Now diode is consuming 0.2 volt for forward biasing. So what will be the effective voltage? 2 volt is the voltage drop across these two resistors, right? So voltage drop across these two resistors is 2 volt, and addition to that, the diode is also consuming 0.2 volt because it is the requirement for forward biasing. So total voltage should be 2 plus 0.2, that is 2.2 volt. Okay, 2.2 volt. So be careful. This is a very interesting question. Even though it is part of the syllabus and it is not actually based on diode concept, only the diode is in forward bias or reverse bias, that is the question. Okay, this is actually based on your current electricity chapter, based on the Ohm's law chapter. Only thing that diode is also there, it is there is some voltage required for its forward biasing, and if the current flowing in the circuit is 0.2 ampere, then only thing you have to do, you have to calculate the total resistance, calculate the voltage, and then add the voltage which is required for the diode to be in forward bias. That's it. Okay, correct? Now let's move on to the question number 13. The energy gap in case of which of the following is less than 3 electron volt. Okay, so we know that energy gap is less than 3 electron volt, that is for any semiconductor, that is germanium. Okay, even though I feel this question is incomplete, because if you consider aluminium, iron and copper, all of them will have energy gap less than 3 electron volt, because 0 is also less than 3 electron volt. So when I discuss this question during my regular class, I added one more line, that less than 3 electron volt but greater than 0. Okay, because 0 is also less than 3 electron volt. So any of the three actually could have been the answer, but as for the sense of the question and given from the given option, we can say germanium is the correct answer. Right? Now question number 14. I don't think too many questions are left for this chapter. An LED is constructed from a PN junction based on a certain semiconducting material whose energy gap is 1.9 eV. Then the wavelength of the emitted light. So this is also based on concept of dual nature of radiation and matter as well as semiconductor. Okay, we know that E is equal to h nu. Also what else we know? Nu is nothing but hc by lambda. Right? Again we know that, remember that in this case the options all are given in meters, not in nanometers. Okay, but what I will do, I will not go into that things that to convert them into meter or nanometer. What I will do, I will put the value of E in EV only. Okay, and HC 1240 electron volt nanometer. Okay, so that I don't have to do a lot of calculations. So I will get lambda in terms of nanometers. Then I will convert it in back to 1240 divided by 1.9. Okay, so after calculating in nanometers, this is a unit for this is nanometer. Okay, I have to convert it into meters by applying 10 to the power of minus 9. Now, if you consider this 1.9 to be very close to 2, okay, so we are doing our approximation thing. So you will get this value to be 620, almost equals to 620 nanometer. 620 nanometers. Okay, correct answer will be slightly more than 620 because we have increased the denominator, right? So correct answer should be more than 620. 620 times 10 to the power of minus 9 meters. Now if you see 620 times 10 to the power of minus 9 meters, we can write this as 6.2 times 10 to the power of minus 7 meters. So correct answer is obviously option D. It will be more than 6.2, as I said. It will be 6.5 in fact, and we just need to change the value of 10 to the powers to check whether it is correct or not. Okay, so our approximation value again survived, our approximation method survived, and we got the correct answer. Now question number 15. In N-type semiconductor, electrons are majority charge carriers, but it does not show any negative charge. The reason is the mobility of electrons are extremely small, electrons are stationary, atom is electrically neutral. This is the correct answer. Electrons neutralize with holes. No, that is not the correct answer. Okay, so this is the last question for this chapter. Only 15 questions are left. Lot of questions that used to be part of digital electronics are no longer part of this chapter, no longer part of the syllabus. Zener diode is also no longer part of the syllabus. So we can expect question based on these questions which are only left. 15 questions that is we have done. So but this is a very important chapter. Historically 4 questions up to 5 questions is coming from this chapter. So if you want to practice these 15 questions. Also during tomorrow's mock test, tomorrow's KPL session, I will be giving you some standard questions from this chapter, and I will be discussing the answers at night. So if you want to learn more from this chapter, then stay tuned. Tomorrow I will be back with the solution for KPL. Till then, bye.